Welcome to iLecture Online, and here's another example of how to find the center mass of an irregularly shaped object. In this case, the object is kind of like a wedge or a triangle. And in this case, we're going to have to use calculus in order to do that. We'll be able to do some integration here. All right. Instead of using the following methodology, that the center mass, let's say in the x direction, is equal to the sum of all the areas of each piece times the center mass of each piece in the x direction divided by the sum of all the areas, we're going to have to snip it up into small little segments. So instead of using the summation symbol, we're going to use the integration symbol. This is going to be the integral of all the little dA's multiplied times the center mass of each dA divided by the sum of all the little dA's. All right, so how do we do that? Well, we go ahead and take a little slice. And this is now going to be called our dA. Our dA is going to be equal to the length of this, which is 1 minus the x position on that line right there. So it's 1 minus x times the height of that little line segment, which is dy. And the x coordinate of the center mass of that area, the x tilde, can be defined as the sum of these two divided by 2. So it would be 1 plus x divided by 2. Now, you may say, well, we have an x here and a dy in the same equation. How do you work with that? Well, we have to find the relationship between x and y of this particular line. This looks like a straight line, which has the equation y equals mx plus b. Now, b will be 0 because it goes right through the origin, so we can forget about that. And the slope is the rise over the run. The rise is 3, the run is 1, so we have y equals 3x. There. So that's the relationship between x and y, which means if we solve this for x, we could say that x is equal to y divided by 3. And so for those two equations, I can plug in y divided by 3 instead of the x. So a dA will be equal to 1 minus y over 3 times dy. And for the x tilde, for the x coordinate of the center mass of the little line segment, is going to be 1 plus y over 3 divided by 2. Okay, now knowing that, we can plug that into our integration. So this is going to be equal to the integral, and I'm going to integrate over the y variable, and the y goes from 0 to 3. So from 0 to 3 of the dA, and the dA is going to be equal to 1 minus y over 3 times dy times the x coordinate, which is 1 plus y over 3. There's my dy, and the divided by 2, I can bring that outside integral sign and put it over there. So this is my dA, 1 minus y over 3 times dy is my dA, and this divided by 2 is equal to my x coordinate of the center mass for that little segment. And I'm going to divide that by the area of that little segment integrated, so the integral from 0 to 3 of my dA, and my dA is going to be 1 minus x dy. Now, of course, if we're a little bit smart about it, we can see that it's fairly easy to find the area of this whole plate, so we really don't need to integrate it, but I'll just go ahead and do it as an illustration anyway. So the next thing I'm going to do is multiply this out a little bit. So this is equal to 1/2 times the integral from 0 to 3. This is the sum and the difference of these two binomials, so we can see that it's 1 minus y squared over 9 times dy, and divide the whole thing by the integral of 1 minus, I wrote x, but actually I want to write 1 minus y over 3, because we want to use the same variable here. So this is 1 minus y over 3. So from 0 to 3, 1 minus y over 3 dy. And now I'm ready to integrate this. So now I'll come over here and do the actual integral. So the integral of 1 dy is simply y, and the integral of y squared over 9 is y cubed over 3, and that would be 3 times 9, which is 27. I still have the 1/2 in front. I can't forget about that. And I have to evaluate from 0 to 3 and divide that by the integral in the denominator, which is y minus y squared over 3. Well, 3 times 2, which would make it 6. I'll put brackets around it, also from 0 to 3. Again, when you integrate this, you get y squared over 2, and 2 times 3 is 6. Okay, now all we have to do is evaluate this. So this is equal to 1/2 times, when we plug in the upper limit, we get 3 minus 3 cubed, which is 27 over 27. And of course, when we plug in the lower limit, you get 0, so you don't have to worry about that. And divide this by 3 minus 9 over 6. Okay, simplifying this, 27 over 27 is 1. 3 minus 1 is 2, so we get 1/2 times 2 in the numerator divided by 3 minus 1.5. So this is 1 divided by 1.5, which is 2/3. So that means that the x-coordinate, which is what we're looking for right here, the x-coordinate of the center mass is 2/3. So where's my, well, I'll use a blue color. So in the x direction, 2/3 is right here. Somewhere along this line is the x-coordinate of my object. So x, center mass, in the x direction is equal to 2/3 of a meter. All right. Now we have to do exactly the same thing, but now for the y direction. So for the y direction, I need a little slice like this. There's my little dA. And my dA in this case is going to be equal to the height, which is y minus 0, which is simply y, multiplied times my width, which is dx. So I need to now express y in terms of x, because otherwise I can't integrate. And my relationship here is that y is 3x, so instead of y I can write in 3x. So my dA is equal to 3x times dx. So now I have my little area element in that direction. Now the center mass is right here, halfway between there and there. So it would be, the height is y, and half the height would be y over 2. So my y tilde is equal to, that would be y divided by 2, and since y is equal to 3x, that would be equal to 3x divided by 2. So now if I'm going to find the center mass in the y direction, center mass in the y direction, that's equal to the integral of my dA's times my y tilde. This is the center, the y coordinate of my center mass divided by the integral of dA. And notice that if I integrate from there to there, because this is the slice I'm using, from there to there, the integral is from 0 to 1, 0 to 1, 0 to 1. Yep, there we go. And of course, it is x equals 0 to 1. Now plugging in what these are equal to, this is equal to the integral of my dA is 3x dx, and I have to multiply that times my y-coordinate of the center mass, which is 3x over 2, and I divide the whole thing by dA, which is the integral of 3x dx, and x is from 0 to 1, 0 to 1. Okay, so what I've done now is I've put in my little area element, 3x dx, and my y tilde. This means the y-coordinate of the center mass, which is in terms of x, 3x over 2. Okay, now simplifying this a little bit and integrating. I have 3 times 3, which is 9, divided by 2. That can come outside the integral sign. So I have 9 over 2 times the integral of x times x, which is x squared times dx from x equals 0 to 1. And in the denominator, I can pull out the 3, and that's integral from 0 to 1 of x dx. And now I'm going to go ahead and integrate those. Those are pretty straightforward. And remember that 3 goes into 9 3 times. So that is equal to 3 over 2 times x squared dx integrated, that becomes x cubed over 3. Evaluated from 0 to 1, divided by integral of x dx is x squared over 2. And that's evaluated from 0 to 1. Now notice I have a 3 and a 3, that cancels out, and a 1 over 2 and a 1 over 2 here, that cancels out as well. When I plug in the upper limit, I get 1 cubed divided by the lower limit, the upper limit here, which is 1 squared. When you plug in the lower limit, you get 0 anyway, so you don't have to do that. And so this is simply equal to 1, which means that the y-coordinate of center mass is equal to 1. So that's equal to this right here, and where the two meet, this is the center of mass of this object. And we could say that the center mass in the y direction is equal to 1 meter. And so the center mass can now be defined as In the x direction, 2/3 meter, and in the y direction, 1 meter. And there's the answer to this problem. And that's how you find the center mass of an object, where you cannot just simply chop it into pieces and find the center mass of each individual piece, where you simply will have to integrate in the two directions to find the x and the y coordinate of the center of mass.